with the technology we have. AGF's part of it. We work with SkyTim, originally formed a Danish company. We work with SkyTim Canada. We have a couple of their crew members here. Fred, raise your hand. Patrick, and then Livewire Aviation, Yacil, and he's helped on ground operations. And over in the helicopter, we have Chase Olson. So we'll get to meet all those guys in a minute. So what's exciting about this is we've had the opportunity to work in the Ogallala Formation, High Plains Aquifer for many years in western Nebraska, Wyoming, and Colorado. So we had a really good idea that this would be wonderful information coupled with the great work that the KGS has done for decades, multiple decades. And you got to think about this. We're using a remote sensing technology. So what does that really mean? It means we're getting an image of the Earth, but it's a little blurry. It's a little blurry. And how do you take away that blur? Is you use good geologic ground control. This stuff, as cool as it is, helicopters, noise, flashy things, it's really going to the core of the geological information that has always been here to bring it to life. And so that's what the KGS is going to be doing for you all, and we're really privileged to be there. So a little bit on where we're flying. We have this image up here. You're welcome to come closer. Some of this is on the district's website. This is the Colorado border. We're here in Colby. We've collected about 50% of this. We have a few more lines to do up here and a few more down here, kind of in the southeast portion of Sherman County and the southwest portion of Thomas County. And it barely clips a little Wallace and Logan down there. We're going to keep moving east as we go. We're probably looking at approximately another week or so of acquisition. Weather is really dependent on how successful we can be. Wind, rain, thunderstorms, and as you guys will see, it's quite a gizmo. We got to keep a lot of moving parts all moving in the same direction. So we'll go and take a look at it. I want to give a little example of how this system works. So everyone has seen metal detectors, right? Has anyone never seen a metal detector? No. Pretty same sort of technology. What we're doing is we're inducing a current that flows around this external loop, and all that loop is holding up the system. It pulses the ground, and then we listen. We listen in microseconds and milliseconds, very small signals. But we're really fortunate. The physics of the Earth is that while we're flying over clay-rich materials, so shales and clays, and even some of the silts, we get a strong response or a high response. When we're flying over sandstones or sands and gravels, we get a low response, so a resistive response. And what we're mapping is the ability of the Earth's materials to conduct electricity. So, simple thing. If I were to take a battery, 2 wires on the ends, and put it on a piece of 2x4, would I get much current to flow through that 2x4? Probably not, right? It's an insulator, right? It's resistive. Now, if I were to take a piece of metal and do the same thing, what would I get? Sparks, probably, right? A few of us have maybe done this on accident. We're changing batteries, right? So that's conductive. So we're looking at those changes with the Earth. How deep do we see? We're seeing about 1,000 feet deep, which is well into the bedrock systems in the area. Most of this area is underlain by Cretaceous pure shale. It's conductive, so that's a great kind of indicator for us to say where the bottom of the aquifer is, which is super, and we're getting data. How quick do we get data? We measure about 10 times a second. And through processing, we get a data point about every 100 feet or so. So when you start thinking about this, we're flying at 55 miles an hour. The helicopter's at 200 feet. The system is at 100 feet. We're mapping down 1,000 feet, and we're getting a sample every 100 feet. That's a lot of data. And that's the key that the KGS is going to use to start putting together the pictures of the Earth. So that's kind of a simple thing. I know the district has one of our videos on. It gives a little more illustrations on how it works. I was going to give just a quick safety briefing. what we're going to do is we're going to take a look at the system. I'll go around and explain the different components with Fred. He'll be helping me with that. And then we're going to all stage in one location, and the crew's going to get it started up, and they're going to take it off for us to see. So we never want to approach the crew in the helicopter when they're operating. So we have two options for staging. We can stage kind of here to the south of this hangar. We'll probably take off and move kind of towards the south so you'll get a good view, or we can stay over by the vehicles. It's kind of up to you. I think we'll probably have a better view right here. So we'll all stay together, and when the helicopter goes, I've got some hearing protection, and like loose hats and stuff. Just be aware of that. And there could be pieces of grass flying around, so keeping your sunglasses on is a good deal. So with that, again, I just want to thank all of you and the great privilege and trust you have in us to help you map some of your aquifers. And at that, questions from anyone? Now there will be a test that we have at the end. So what do we measure in? Do you even remember what kind of seconds we measure in? I mentioned milliseconds, microseconds, very small. About how deep do we see? 1,000 feet. They were listening, Jim. They were listening. All right, you guys, if you'd like to come along.
Okay. So basically, the way it works, it all starts with power. We need power, so we have a generator out there that provides power to the instruments in the front that we'll see later, and which we use to power this cable, which is the transmitter loop. So that's where all the energy goes into to create that field. And then what we measure from the response from the Earth happens in the top of this tower. There's a receiver coil, kind of like an old stereo radio antenna. A bunch of wires coiled around a square thing. It's the same kind of antenna inside of that that's pointed in this axis. And we have another one, that bubble in the back, that sees the x-axis. And so these will pick up the smallest responses from the Earth, from the current that we generate, and then they will pass it on to our instruments. It's analog signal, and it gets converted to digital signal to be recorded on a computer, and then we can interpret this data with computers and stuff.
A couple keys to the way this system is designed and why it's successful. This is what's called a null position sensor. So everyone's seen the diagrams of bar magnets. We got north and a south pole, and the fields go around it. Everyone's seen that, right? Well, this loop is kind of like a big magnet when it's energized. And when it's going like that, we have lots of power. So these receivers can be saturated, meaning they're seeing all this power. Well, that's going to defeat the purpose, because when they saturate, they've got a recovery, there's a recovery rate, there's some non-linearities. Here's the fact of it, it's no good. So Kurt Sorensen, who designed this system, said if we were to position this very precisely in the null space, we can turn the amplifier up high and look at those very small signals without saturating electronics. So this top fin is the Z component or Z component. That's the one that's really our hardcore working current, or our measurement that we use for these aquifers, because they're mostly layered, sedimentary layers. The X coil, as Fred mentioned, is really good on edges, and we use it for looking at edges and stuff. But by using this null space system, we can really turn the earphones up, really turn up that gain to see very small signals. How small? Nanovolts, picovolts. Very, very small. So what's also important is this non-conductive frame. Starting from right here back, there's virtually no metallic components here. These are all fiberglass and synthetic ropes and bolts, because any of those pieces of metal can cause noises. Why do we keep this system 100 feet below the helicopter? The helicopter is made of metal, right? We don't want to just see the helicopter. We want to see the earth. Now, when we're flying along this stuff, guess what we do see? Power lines, pipelines, every single one of them. So we'd be very careful to try to cross them perpendicularly and not fly down them. And those data at those points we actually remove. We do it in a process called decoupling because it's coupled to the wire. The 60 hertz and its harmonics we can tune out. There are digital filters in the system, notch filters, that remove that, but it doesn't remove the inductive coupling we give to the wires. So it's the nature of doing this type of work. So we plan around that. So the best way to think about these systems, and it's governed by, we call it diffusion equation. Basically, it's a smoke ring. So we energize this current and then we shut it off very abruptly. At that point, the field collapses. And what happens in physics is that field collapses, everything's pushing to try to keep it in steady state. So opposite currents start forming to make up that difference. At time zero, when we turn it off, it's exactly the size of the loop, which is why we need to know precisely where this loop is positioned. And Fred will show you our guidance system. Then as it goes deeper, it spreads out and gets wider. So shallow at the top, wider as we go down, and spreads out. So at the bottom of 1,000 feet, we're seeing probably 5 times the width of this system at depth. Now, that's important for the KGS people. As the deeper we see, the coarser our resolution. So we need to take that into account when we're looking at hydrogeologic parameters, how we match it up to lithology, and what that says about how well water will move through that, because we're starting to get a sum. So it's just like taking whoever's put together circuits, resistors and stuff, capacitors, and a little thing. We did Boy Scouts or college or high school, same sort of thing. That's the way the Earth is built. All these capacitors and resistors, but if you sample widely, it's a sum of all those. So that's exactly what happens. So it's not magic. It would be a lot easier if it was. My gosh. So, but the key is we're building maps. By getting these 100 feet between samples, we can start seeing details and how they change spatially at a density. We couldn't do it on the ground. We couldn't do it with drill rigs ever. So, all right, Fred. Shall we go up towards the front?
Okay, so at the front, like you see, you can come closer. There's no danger whatsoever right now. It's not on. There's no electricity flowing. So here at the front is all the electronics. So the way it flows, so basically the generator charges this box, which is full of capacitors, so it stores energy. And then as we give impulses in that big wire, this is the transmitter that is responsible for outputting the signal into the wire. So we have a dual moment system. So we have what we call a high moment and a low moment. So it's actually switching between the two. Alternatively, so like the high moment will see deeper and the low moment will see shallow, because it's very basically it's like 9 amps or 10 amps for the low moment, and we're talking about like 110 amps for the high moment. So very different levels of energy. So this is just how the current flows. Then we got a cooling unit, because this gets really hot as it transmits high power. The electronics get hot, so it needs to be liquid cooled. So we got a cooling unit just for that. And then this one is a bunch of sensors, inputs, and computer and all that stuff. So what we got for navigation is we got 2 GPSs on the side there, which will give us a very, very precise indication of where exactly over the Earth the system is at every time. There's 2 for redundance, so in case one fails or is a little bit less precise than the other one, so it's only for redundancy. Then we got these 2 on each side. There's laser altimeters. GPS position and stuff will give us like a really good, precise indication of how and where the system is positioned in space at any given time, and that really is very, very important in the processing aspect of the data. Then we got in the front over there, so the reason for this long spear is because in the front we have it's actually a different survey instrument. It's a magnetometer. It's a very common instrument that simply measures the Earth's geomagnetic field. So that, again, coupled with the GPS location and the position in the air and stuff, will give us another kind of spectrum of information. So some companies will actually fly surveys just of mag, and it's usually in the shape of like a little rocket-looking thing that's hanging below a helicopter, or even flown with like fixed system on an aircraft. But this is in itself, it's a specific type of survey. It doesn't give as much information, or not the same type of information as this technology, but it's basically really easy to do the two at the same time. So it's additional data that's very valuable. And the reason why it's on a spear that long is just to keep it away from all the electronics and all the noise that's happening here. So yeah, do you want to add anything based on?
Yeah. So in this part of the world, we're seeing very deep. We're seeing well into the crust of the Earth, up until the Curie point, where it gets too hot and the magnetics goes away. It's not terribly useful for the aquifer mapping, but what we do use it for here is it helps us see man-made materials, because ferrous metals. And ferrous metals are usually where we have coupling, pipeline, and such. So that's really good to see. Now, in other areas, not necessarily here, but in other areas of the U.S., it's very critical because it's another view of the Earth. So we have the resistivity, then we have the magnetic properties. So we always fly it simultaneously. It'll be part of your archive in the state. I mean, there has been surveys flown for magnetics in Kansas over the years to look at crustal deformation and deeper seated faulting. So we'll get a lot higher resolution. So now, here's the test question. I said we needed to know precisely where we are. Fred said how we do that. Why did we need to know that? Remember what I said? So I said at time 0, we have an exact current filament, the same size of this. So if the loop is tilted a little bit, that'll change that size. So that's really critical. The GPS, they're so good anymore, we're well located within that 100 foot. But we really need to know exactly where that position is, height and tilt and such. So, system, any ideas on what it's made out of? Fiberglass, yep, and some carbon fiber. But you notice it's not circular, it's a little kind of dished out. And that we get a little bit of lift with that. So I think we're gonna run around. You guys are welcome to come and just, don't put weight on it, but you can touch it and feel it. It's very light stuff. Because again, all this frame is doing is holding this black wire up for us. So you notice we got kind of the orange ropes that holds it from going out. And then the white ropes, as we lift off, you'll see. So what you'll see, I'll give you a heads up. They're going to start the helicopter, start the system. Then the helicopter is going to move in. They're going to hook up to that. And then they're slowly going to come up with a helicopter. And you'll see the system kind of come up and tilt. They'll check all the cables and it'll be hanging kind of crookedy. And you're like, they're going to fly that? Well, when it gets enough airspeed, what you'll see is that system will drag back and be really level. So these ropes, Fred and his crew pick the ropes based on the velocity or the speed we're going to be flying. So it's all part of keeping that as stable as possible. Any questions?
How much maintenance does this setup require? Like how often are you having to check a GPS issue or a capacitor? Or...
It varies. Of course, there's a lot of parts, and it's electronics. It's a lot of things that can fail. But I would say it's gotten very, very stable with the years. Like once in a while we'll get something that kind of acts funny, but we got replacements for pretty much everything you see here. So we just swap it out and test it in the like while he's flying or on off days or whatever. Then we'll test out the equipment that's gone bad. We get replacements shipped from our headquarters in Denmark whenever we need to. As an example, on this survey, we had a navigation system die on us, and so we had to change that like last week. So it happens. There's a lot that can go wrong. But in terms of maintenance, we can fly a whole survey. Everything stays the same, and it doesn't require maintenance per se. Aside from the generator, of course, it's an engine. It's running a lot of hours per day. So we do like basic maintenance on there, like oil change, spark plug, and basic stuff. That's pretty much it. Then maintenance on a helicopter, of course, it's like just the typical inspections and required maintenance.
Best data quality we can. He's got a lot of things going on when he's flying, but he helps guide us through that infrastructure and those coupling areas to get us the best data, keeps the system level, and really makes it happen. He's with Livewire. I've known the folks at Livewire for many years. As a friend, I think from 2013. One of the amazing things about the system, the way it was designed, is there's no permitting and clearance that has to be required for aircraft. The other day we were flying with a different aircraft. We switched aircrafts out for a maintenance issue. We can just switch out a very simple, I'll let Fred explain kind of the navigation system, how simple it is to install.
Yeah, so basically what I forgot to mention, the navigation instruments on the loop, so the GPS data, the laser altimeter data, and the pitch and tilt of the system is all transmitted in here to the pilot on the little screen through a radio antenna that's mounted on the front of the system. We have another radio antenna in here, and it's routed to this PC. It's basically just a computer, and it's feeding that info on a display that's mounted right here for the pilot to actually look at, because he needs to respect the height, and he needs to keep the frame level, and he needs to adjust like every few seconds, make corrections according to the wind, the direction of the line, and all that stuff. It's very hard work, but to do that, he needs that information. So it flows through radio communication, basically kind of like Wi-Fi, if you will. So it's only just a box, and we have some little arm mounts that we just clip on there. And in helicopters, there's a power port and an auxiliary power port that's built especially for the purpose of powering external equipment. And since it's the only power that we use from the helicopter, like Jared said, we don't need any kind of special permit to get this installed in the helicopter. As long as it doesn't move and it's well secured in place, the FAA will look at this and say, yeah, all good, no problem, it's only temporary. And since also the system can be detached, it's treated just as an external load. Just like anything else on a long line, so that's really a key feature of the SkyTem system.
Yeah. So Chase, you want to tell them a little bit about the aircraft and kind of how it's for you flying?
This particular aircraft that we primarily use for these projects, this is a Airbus AS350 V2 variant. We have a few other different variants, but they're pretty much the same size of helicopter. This aircraft gives us a lot of performance, basically to lift the system. The lift system weighs sometimes north of 1,300 pounds, and we're flying it relatively slow, so we need that power margin in this aircraft. These type of aircraft give us that margin to fly it. As he pointed out, as we're flying a system, we have a grid laid out. I usually use two different systems. I have a KML file that I have fly off my navigational GPS. We just use an iPad through ForeFlight, and then the SkyNav system. I basically kind of use both of those to correlate with each other. Like I said, when we're flying, basically keeping the aircraft, the speed, and the loop in the parameters to give us basically the best data. And sometimes we have to, accommodate, make adjustments for the wind. Obviously, the altitude and stuff is always somewhat changing, and just like I said, basically just trying to keep the aircraft and the loop in within parameters to give us the best data that we can possibly give for them.
So you've been doing this quite a bit for us. Yeah.
I have. I've been flying about 17 years now. I started out flying these systems up in Alaska with SkyTim, working with a company called Saloy Helicopters up there. And then I've bounced all over the country, basically doing all kind of various utility projects, including these along the way. And with Livewire, being SkyTim, one of our contractors that we work with, we've been working with them pretty much solely, pretty steadily for a while now. And of course, Livewire Aviation does a lot of other various utility jobs involving other helicopters as well. So kind of get to bounce around. I'm actually the chief pilot for Livewire Aviation. So I bounce around. I actually train other pilots to basically learn to fly this system, to learn to fly the airframe, and all our other basically job scopes that we perform.
So how many people are in the helicopter while you're surveying?
Just me.
Okay.
Yep, it's just me. This is technically, as it's set up now, is a 6-person helicopter, but doing external work, unless you're essential to the function of basically the job task, at that point it's just me.
Sometimes, so it's fortunate in Kansas the terrain is fairly flat. There's not many infrastructures and stuff like that. That gives you a much better data set, just because it's a lot easier to fly and keep the parameters very, very tight and very close to the ground and everything. But if you imagine trying to keep 100 feet off the ground in mountains, or like, you know, big valley, or you know, very kind of like big forest where the topography changes a lot and there's a lot of infrastructures and stuff, then it gets very, very different. Let's say it's a lot harder to fly, but yeah, for you it means great data because it's flat, and for us flying with these guys with Livewire, with experienced pilots that are used to fly utility, so they fly aerial saws, they fly you know, big piece of equipment on a long line with very, like, really good precision. So we require that level of skill to fly our system. Not any pilot can just pick it up with a helicopter. Like, it doesn't work that way. You need the skill, you need the time and precision to be able to fly properly. And these guys provide it, so that's really good. And that's all working towards getting you guys much better data, actually. So this is a very, like, perfect perfect conditions for this type of survey.
Well, shall we give them a show, guys? Get her going? We're going to collect data too, but so All right. Any other questions, everyone?